Next is electrophilic addition reactions. And this would be going into some HO content, but 3.3.4 and 3.3.5 is SLHO, and 11, 12, 13 is HO. So let's start with the SL content. Electrophilic addition reactions. Oh, just a note, to me, the HO content is pretty similar to the SL content. It's mainly just an add-on, so the SL content is what you really have to know. Electrophilic addition, okay? So electrophilic, electro is electron, and philic is loves, and addition is adds. So if you break down, it means that it's something that really loves electrons, meaning that it's electron deficient. Or the valence shell is not filled. Okay, so it wants electrons. And so it's something that loves electrons, and it will add on to a molecule, okay? One key example, let me pull up my examples, wherever that went. I have to find the file. Oh, I hate it when my Mac does this. Sorry about that. Yada yada yada. Electrophilic addition reactions. So let's use a keynote. It will only happen in double bonds. So if you already learned organic chemistry, or structure 3, then you would know it's something that ends with an ene. So ethene, methane, propene, butene, and stuff. Yeah. Okay. So let's use ethene as an example. Sorry about that. H plus a hydrobromine. Okay. So this is a classic electrophilic addition reaction. So let's focus on the hydrobromine first. We know that bromine has pairs here, so this would be partial negative, and this would be partial positive. And essentially what happens in an electrophilic addition reaction is that the double bond breaks apart. So you would have C, H, and H. And you have to know that this will form a carbocation, meaning that this is partial positive, and this is, you just have to know that this is partial positive, and think of it as having an extra bond here, because carbons need bonds, okay? But we'll focus on the carbon on the right first. So what will happen is that the hydrogen bromine would form hydrogen and bromine, negative, positive. And this bromine, because of its negative nature, it will want to react with something positive. So it'll go here. You would then form CCH, the Br right here. Okay. But then you're still left with an empty bond, which then the hydrogen will come in and fill this place from this. So your end product would be CC. It's probably not supposed to be drawn like this. H, Br. You end with a bromoethane. Okay. So as you see, the double bond broke down, and the bromine with a negative charge would go with the, let me get my little pointer. The negative charge would react with the carbocation because it's attracted due to its charge, which adds in, and the hydrogen would then fill in the extra blank. So this is where an electrophilic addition reaction happens, okay? It's an addition. And electrophilic is mainly driven by electrons. Some key points to note about this is that atoms grow in size. Oh, molecules grow in size. This is easily deduced because double bonds have a stronger pull, or a stronger LDF. So if it breaks down, it would actually be a bit longer. And the bromine comes in, adding mass. The hydrogen comes in, adding mass to the ethane. So it will increase in size. Another thing to note is that because it's an electrophilic addition, if there is a full octet, nothing will happen. So meaning that there is no reaction. 3 things to know is halogenation, hydrogenation, and hydration. Okay, and you can all look at what happens from the name. So you don't really have to care about the nation. What you want is the first half. Halogenation means it's a halogen. So group 17. So elements like bromine. No, not bromine. What could there be? Chlorine, bromine, fluorine, iodine, etc. Hydrogenation is hydrogenation, so you add in a hydrogen plus a halogen. Okay, so HBr, hydrochloric acid, HI, or HF. Okay, so they're adding in these hydrogen plus a halogen. Lastly, hydration. Hydration, when you drink, you hydrate, so H2O. You add an H2O. These are what could happen in electron addition reactions, okay? Or electrophilic addition reactions, okay? So this is the SL content. Now let's go into a bit of the HL content. This is where it gets a bit repetitive. The 3.4.11 is electrophilic addition of alkenes. Okay, which is exactly what we've just talked about. So for an example, you start with a double bond reacting with an alcohol. It's an OH group, and this is an ethene group. So C double bond, okay? This is just gonna deal with organic chemistry. So, and also symmetric alkenes. Symmetric alkenes, okay? So let's use ethene again. Okay, so use ethene plus an OH minus for simple things. So what will happen is that the O is partially negative, H is partially positive, as we discussed in other videos, because here, just to visualize it, and there's electrons on the O, so it's negative, no electrons on the H, so positive, okay? So what will happen is that the OH, the bond will break here, the OH will move in and add in, so and then let's see what else. Hydrogen. You may wonder where this hydrogen comes from. This is where a catalyst also comes in. A really usual one is H2SO4. Okay, This is essentially just a catalyst. So actually this would be H2O, actually, not OH. Sorry guys. H2O, so this would be OH2, and then however, because an oxygen can't have 3 bonds, the H would go away and go back to H2SO4. Just note that it will be a catalyst of H2SO4. Nothing important, but just know that. And then that's really it. Just make sure that an alcohol is added in when you add water or H2O, and you need a catalyst like H2SO4. Bad explanation from me, but you get the general point. And this will always form one product, because no matter if the OH goes to this carbon, let's use pointer. No matter if it goes to this carbon or to this carbon, it'll be the same thing. It looks flipped, but it's the same thing. You have to think in a 3D world, okay? But then if there is an unsymmetric alkene, there will be 2 products. Because the OH can go into different locations. So let's say there is a, what's this? Butene. Butene, double bonds here. Double bond will break here. The OH can either go with this carbon or with this carbon. It doesn't really matter, but then something to keep in mind is that what will most likely happen, okay? They both will happen, but there's one that's more likely to happen. Let's get a new page. So C double bond. So we know that there's hydrogen, hydrogen. So this would be, let's see, how would this look like? This would be partial negative, partial positive. So you see the carbon in the middle is surrounded by 2 other carbons, meaning that it wouldn't really like to form because, well, it's a really bad explanation. How do I explain? This will less likely form because this charge is, this is more partial positive than this carbon, so it will always go to the more positive one. I know this explanation isn't the best, but then here's something that would also help you, which is the Markovnikov's rule. It's a Russian scientist, basically. But all you have to know is that he states that the carbon attached to more will attack. So once this is broken down, same amount of carbon. Okay, it's fine. So more carbon, if it's attached to more carbon, it's more stable, so it would want to react less. But the carbon on the left here, let me get my little pointer. Carbon on the left here, it's attached to more hydrogens compared to carbons, meaning that this carbon right here would more likely to react. It's less stable, whereas this carbon is attached to more different carbons, which makes it more stable and it would less likely react. Easy way to remember this is rich get richer. Okay, rich get richer. So rich in hydrogen, it will get more hydrogen, and poor in hydrogen will get less hydrogen. It's really simple. And that's really it. And then now there is electrophilic addition with benzene. Now, this is something you would have to know, definitely have to know. So, essentially, how should I say this? A benzene ring. Benzene, oh, it's not a benzene ring. Benzene ring, so it has 3 double bonds like this, and the rest are hydrogen. Okay, and this is an electrophilic substitution reaction. Okay, so you see this is a benzene plus an electrophile. E is an electrophile. Essentially, what happens is that they both want electrons, both the electrophile and the benzene, because there's the 3 delocalized electrons going around, acting as a resonance, so it makes a resonance structure. But just know that they both want electrons. They're both electrophiles. Okay? And what would happen is that the electrophile, so let's draw another benzene ring. Electrophile will substitute in this and plus a hydrogen or a proton. Hydrogen ion will always be a proton because it only has 1 electron, so you get the point. So this is what will happen. The electrophile will substitute in and you'll get this. A way to think about this is that you're in a table and an elderly wants to sit beside you, so you guys sit together on a chair, but eventually you feel comfortable and you leave and you let the elderly get the chair. Elderly, which is the electrophile, and the age is you, so you guys you leave for the elderly to sit, and yeah. Key points. The intermediate is when both hydrogen and electron is there. So if we go back to what I just said, you and the elderly are sitting on the same chair. Okay, you guys are both there. This is the intermediate. And then it'll form the H plus. Just some more things. You need really high activation energy. The key points. You need high activation energy. There is an intermediate. Form, and it forms fast. And then when the final product is formed, it's slow. So overall, your reaction would be slow. Just keep that in mind. And that's it for electrophilic addition and substitution.